Millions of people make phone calls at the same time. Billions of devices connect to the internet every day. Yet, they don't all need their own dedicated communication channel. So, how can thousands or even millions of users share the same network simultaneously? The answer is multiplexing. In the previous lesson, we learned that every communication channel has a maximum capacity determined by its bandwidth and signal-to-noise ratio. Since communication resources are limited, another challenge naturally appears. Imagine if every smartphone required its own dedicated radio frequency. Modern cellular networks would quickly run out of available spectrum. The same problem exists for Wi-Fi, satellite communication, television broadcasting, and fiber optic networks. This creates a fundamental engineering question. How can many users share the same communication medium without interfering with each other? The solution is a technique known as multiplexing. Multiplexing is the process of allowing multiple independent signals or users to share a single communication channel efficiently. Instead of giving every user a separate physical channel, multiplexing divides the available communication resources so that many signals can coexist without significant interference. The most common multiplexing methods include frequency division multiplexing, FDM. Each user occupies a different frequency band. Time division multiplexing, TDM. Users transmit during different time slots. Code division multiplexing, CDM. Users share the same frequency and time but use different codes. Orthogonal frequency division multiplexing, OFDM. Data is transmitted simultaneously over many closely spaced orthogonal subcarriers. Each technique separates users in a different way while maximizing the use of available communication resources. Intuitively, imagine a 4-lane highway. Instead of building a separate road for every vehicle, thousands of cars safely travel together because each follows its assigned lane. Multiplexing applies the same principle to communication systems by organizing users so they can share the same infrastructure. Physically, consider a cellular base station serving hundreds of smartphones. The network assigns different frequencies, time slots, or resource blocks to different users. Although everyone communicates through the same cell tower, carefully managed multiplexing prevents users from interfering with one another. Mathematically, multiplexing divides the available communication resources into orthogonal dimensions, such as frequency, time, or code. By ensuring these resources remain distinguishable at the receiver, multiple information streams can be transmitted simultaneously through the same physical channel. Multiplexing is one of the most important technologies in modern communication systems. FM radio stations share the spectrum using frequency division multiplexing. Digital television uses multiplexing to broadcast multiple programs efficiently. LTE and 5G rely heavily on OFDM to support high-speed mobile communication, while fiber optic networks use wavelength division multiplexing to transmit enormous amounts of data over a single optical fiber. RF engineers continuously optimize multiplexing strategies to increase network capacity, reduce interference, improve spectrum efficiency, and support the growing number of connected devices worldwide. Without multiplexing, today's wireless networks could support only a tiny fraction of the users they serve every day. Multiplexing demonstrates that communication performance depends not only on faster hardware, but also on smarter resource management. By sharing communication channels efficiently, engineers dramatically increase network capacity without requiring additional spectrum. A common misconception is that every user receives a dedicated communication channel. In reality, modern wireless systems dynamically share available resources among many users, allocating bandwidth, frequencies, and time slots as needed. Now that we understand how multiple users share communication resources, we are ready to examine complete wireless systems. In the next lesson, we will explore wireless systems, Wi-Fi, LTE, and see how all the concepts we've learned come together in real-world communication networks. In this lesson, we learned that multiplexing allows multiple users or signals to share the same communication channel efficiently. We explored the major multiplexing techniques, including FDM, TDM, CDM, and OFDM, and saw why multiplexing is essential for modern communication networks. In the next lesson, we will explore wireless systems, including Wi-Fi and LTE, and discover how real communication systems apply these concepts in everyday life. If you found this useful, like the video, subscribe, and follow for the next lesson.